starting the session. And in this session, from like till 4:15, we will discuss the tests to compare the mean and median. So basically, we'll be seeing the independent sample t-test, its non-parametric counterpart, and paired sample t-test and its non-parametric counterpart. So to begin with, so by this time we have learned the categorical variable, the association between the categorical variable, and then seeing the association between the continuous variable, that was the correlation, and we have learned the descriptive statistics. So now another type of this tests in the inferential statistics are the group of t-tests. So in this group, we have got the independent sample t-test where we compare two means. We have got its non-parametric counterpart, which is the Mann-Whitney test, where we compare the median. And then we have got like paired sample t-test where we compare two related means or the pair data, like same as McNemar. But in McNemar, we were comparing the categorical data. Here we are comparing the continuous data, the pre and post. And then its non-parametric counterpart, which is the Wilcoxon signed rank test, which compares the rank. That's why the name is the like Wilcoxon signed rank test. And you can report the median also in this case. So now coming to the first type of test, which is the independent sample t-test. So if you see, there are three words in this. The first is the independent samples. So the independent samples are like the same concept because they are the two independent groups. And here also that assumption of the independent observation, that will hold true. And the next is the t-test. So t-test is what? You are comparing the mean value, and hence these statistics which the software yields, that's the t-statistics. And based on the t-statistics, it calculates the p-value. That's why it is known as the t-test. So it is an independent sample t-test because there are two independent groups, and we compare the mean value of a continuous variable or a scale variable across group. That's why it is known as the independent sample t-test. Now, what are the research questions for which we can use this test? So the first research question could be, is the average BMI value of a population with history of cardiovascular disease is different from population without history of cardiovascular disease? Is the pain score, which I have measured on visual analog scale in the surgical technique 1 and surgical technique 2, is there any difference in the mean score of these, pain score? Then I will use the independent sample t-test. Or do the medical UG students, like who have got good quality of sleep, they score high in exam as compared to the poor quality of sleep? So in all these examples, what can you see? That there is a continuous variable. So this average BMI value, this is a scale variable. And we are comparing it across two groups, with history of CVD and without history of CVD. In the second research question, this pain score, that is a continuous variable or a scale variable. Like Dr. Farzana, you are asking COVID positive, COVID negative. But what is the variable which you are testing? Like you are writing first follow-up and second follow-up of each group. Okay, if you are measuring BMI in COVID positive, COVID negative, yes, independent sample t-test. And if you are measuring this BMI in first follow-up and second follow-up, it will be your pair t-test. Yes, you are right. So like comparison of pain score on visual analog scale in the surgical technique 1 and surgical technique 2. So these are two categorical variable, and we are measuring a continuous variable, which is the pain score. Again, we will go for the independent sample t-test. And your third one will be your, like the continuous variable in this case is the marks. So score high in exam, or what is the mean value of the score in students who are having the good quality of student and in students who are having a poor quality of sleep. Not good quality of student, like good quality of sleep and poor quality of sleep. So in all these things, what we have seen, that there is a continuous variable and we want to measure the mean of this variable in the two categories of a nominal variable. So what is the choice of the test? So the appropriate statistical test in such cases known as the independent sample t-test, also known as the unpaired t-test. So independent sample t-test, it is also known as the student t-test, between subject t-test and unpaired t-test. So there are three research designs which are possible. So the first is like mean, if you want to see the mean difference between the two independent groups. In all those research questions, we have seen that there was a continuous variable and we were measuring the mean value of that continuous variable across two different categorical variables. For example, this is the data set of like 7 people. And here you can see that there is a male and female gender in the first column. And in the second column, it is the cholesterol level. So if I want to measure the mean cholesterol value in the male and female, so in that case, I may go with the independent sample t-test. The second type of research design can be if I want to know the mean difference of two interventions. For example, I have got this one, there's a group which is an intervention group, and there's a group which is a control group. And I have got the cholesterol value of these two groups. So if I wish to measure the blood cholesterol value after 6 weeks of exercise training program, then again here the variable, this is a continuous variable or a scale variable, and I am measuring this across two categorical variable, which is the intervention and control. So I'll use the independent sample t-test. And then your next is the third one, which is the mean difference in the change score. So how we will do that? So in that mean difference, you can see like if you have got the pre and post, both values. So in this case, if you see the first column, it represents the pre-intervention cholesterol value in the intervention and control group. And this column represents the post-intervention cholesterol value. And this is the difference. So in this case, what the third one, initially we have seen the other two independent sample t-tests like a pre and post cholesterol, but the ideal would be if you measure the difference, means what was the change from the baseline. So for that also, you can use the independent sample t-test when you will just measure this mean change in the intervention group and the mean change in the control group, seeing whether there is any statistically significant difference between these two or not. Then we will go with this independent sample t-test. Now again, since it is an inferential statistics, we know that we will have a null hypothesis and we will have an alternate hypothesis. And we will have to check the data, whether we can go for independent sample t-test or not. So for that, we need to have some assumptions. So what are those assumptions? So the first assumption is there should be one dependent variable which should be measured on a scale variable or a continuous scale. Like in all these examples, you have seen that marks obtained or BMI or the VAS score or the pain score, all those variables was measured on a continuous scale. And the second assumption is like that there should be one independent variable having two categories. So the independent groups can be gender, it can be like poor quality or a good quality sleep, it can be like surgical technique 1, surgical technique 2, or it can be like history of cardiovascular disease or without history of cardiovascular disease. So that other independent group, that should be dichotomous variable having two categories. And then the third assumption is like it should be independence of observation, like the way we have learned in the chi-square, that both the two groups should be separate. If we have counted one person in one group, that should not be counted in the another group. So it should be two independent groups. And then next is your dependent variable. Again, this independent sample t-test, one of the assumption is like correlation, that it should be approximately normally distributed for each group of the independent variable. And that we'll see how to test for that. And the fifth assumption is like there should not be any significant outlier in the two groups of the independent variable in terms of the dependent variable. And this we check with the help of descriptive statistics. And then the next assumption is regarding the homogeneity of variance. So what it assumes that since there are two independent groups, so it assumes that these two independent groups are representing two different population. So it says that the sample which you have withdrawn from the population, those two populations are having equal variances. That means variance is equal in each group of the independent variable. And this homogeneity of variance, this we test by a name test known as the Levine's test. So this normality testing, we have learned how do we do it. If the sample size is less than 50, we go for Shapiroval test. If it is more than 50, we go with the QQ plot or the histogram and density plot. Means we go by the subjective way of assessment. And if the sample size is less than 50, we go by the objective way, which is most commonly it is the Shapiroval. Now, what is the concept of normality for t-test? So in t-test, what we do, we see the distribution or the normality across the two independent group. So the first thing is, we say that t-test is a robust test. So that's why even if the data is not normally distributed, like the term approximately word, the way we have learned in correlation. So if it is approximately normally distributed, then also you can go ahead with the t-test, independent sample t-test. The next is here, if you have got enough sample size, adequate sample size, then the central limit theorem says that even if there is a non-skewed data, it can be tested using the t-test. And there's another very interesting point. Assumption is like, if the direction of the skew is same in both the group, then also you can go for the independent sample t-test. That means, like, if we'll see this again when I'll demo this, but if the direction of skew is towards the same, means both the group, but the dependent variable is having a skewed distribution across both the independent group, whether it is a right skew or a left skew, then also we can go with this independent sample t-test. Now there's another concept which is the homogeneity of variance, which I was talking. So homogeneity of variance says that the variances in both the population, both the independent groups from where we have drawn the sample, they should be equal. And that is tested using the Levine's test of equality of variance.
What do you mean by equal, ma'am?
Remember,
Variances, you will have two separate populations. Variances will differ, ma'am.
but assumptions, if the variances are different, by default, if you see Jamovi, unequal variances, they check that they expect it can be same or it can be different also. It depends. Like it depends from the population also. From where I have variances it is not always because see, if I have gone to a village and I have selected sample, suppose if I have gone to a village and selected all the sample from the same village, because my sampling frame was that single village, there is a lot of possibility that variances will be equal, the male and female, if my two groups are male and female. But if like I have done a state my sampling frame is very big, probably I have selected 3, 4, 5 districts and I have done a multi-state sampling and I have got the representation from all these selected units, or probably if my study is a multi-site study, okay, so then also my
Exactly, ma'am.
population,
If I'm doing a multi-centric study
yeah,
involving Punjab as well as Tamil Nadu,
yeah,
where populations are different,
yeah.
how can you, variances to be same, ma'am? How
that
can you
that
assume?
that that I don't say that, you have to check with the statistically. I mean, I'm not saying, that's why we assume in the null hypothesis that it is having a same variance, like population are having a same variances. That's the null hypothesis, because see, we cannot assume anything in statistics. You have to test it with the given set of tests which is recommended to test these assumptions. So
Suppose, ma'am, you don't get, ma'am. Then what do you do?
So we have got the Welsh, na? That's the option. Another option which it gives that if the assumptions are not equal, then you have to, rather than reporting the standard T, there's another T which is known as the Welsh T. We report Welsh T instead of, because it takes some correction into account in that Welsh T related to that variances. So instead of standard T, we report Welsh T when we check the data. If variances are unequal, and there are chances that even in a single sampling unit, there can be unequal variances or there can be equal variances. That you have to check how your data is behaving or how you have drawn your sample. Did you get it, Dr. Ravi? Not convinced?
Yes, ma'am. Convinced.
Means, like, see, there is something which is, you anticipate something, okay? But even if you have anticipated that, yes, if it is a multicentric study and you are expecting the variances to be unequal, then also you have to show it statistically. You have to check it. You have to, like, it's an objective way. Rather than subjective, we are going objectively. And one, you can mention, like, it was assumed, you assume that variances will not be. That's why you will see when I'll go with this t-test now, by default, it's the unequal variances which it takes, because it also assumes that it will be unequal. But again, then you can, by seeing the value of your Levine's test of equality of variance, you can check, and then you can report a particular T, whether it is a standard T or a Welsh T. So that's what I was about to tell. Like, Jamovi gives two types of independent T statistics. The first, if there is a equal variance, then you use the standard T statistics, its degree of freedom, and the p-value. But if it is unequal variance, then you report Welsh T statistics, its degree of freedom, and p-value. So what is the null hypothesis? Null hypothesis states that the population mean of the two groups are equal, and the alternate hypothesis states that the population mean of two groups are not equal. So this is the independent sample t-test. Then coming to Mann-Whitney-U. So in the Jamovi, on the same interface, you will see that you have got this, because if you see the SPSS, there you have to go separately for this non-parametric test. But here in Jamovi, on the same interface, you get the non-parametric part of this independent sample t-test, and that is known as the Mann-Whitney-U test. So, like, if you expect, like the way you said, like, you know already that there will be variance, unequal variance. Similarly, there are many data sets where you know that, yes, there will be a lot of variation. Like we have seen per capita income. There will be, it is never normally distributed. It is always skewed. Similarly, if you see like SGOT, they also have a quite non-normal distribution. So if I want to compare the mean SGOT of alcoholic liver disease and non-alcoholic liver disease patients, I might face this problem, like the data is not normal distributed across the two dichotomous variable. So in that case, I cannot go. Again, I can go with the independent sample, because I said in the beginning that the normality concept in case of an independent sample t-test is, even if the direction of skew is same in both the groups, still you can go with this independent sample t-test. So here, either you already know that your variable of interest does not follow a normal distribution, but again, even if you know already, you have to prove it objectively across the two categories. So you go with this option of Mann-Whitney-U test. And this Mann-Whitney-U test, if you see the assumption, it is usually used when the assumptions of t-tests are not met, like non-parametric test. So if it is not normally, if the direction of the skew in both the group are different, means in the one group it is left and in the one group it is right, then you can use this. And again, what it does, basically, it arranges the sample in a rank order. So rank, like it will put it in the ascending order. and then it will give a rank, and it compares the mean rank of continuous variable across that dichotomous variable. So the research question, the same variable, instead of rank or instead of mean value, we generally compare the median of continuous variable across two groups. It can be a SGOT level across the alcoholic and non-alcoholic fatty liver disease, or it can be a post-operative pain in the two technique 1 and 2, or it can be a Apgar score in the normal vaginal delivery and the cesarean section. So in all these sets, what we have seen that there is a scale variable which is not normally distributed, and I want to compare it across the two category of a nominal variable. So the appropriate test is the Mann-Whitney U test, or also known as the Mann-Whitney test. So there are assumptions are again, it's the T opposite to T test, means whatever assumptions of T test, if it is not met, then you go with this Mann-Whitney U. So the dependent variable should be measured. It is the same as T test, that it should be measured on ordinal or a continuous scale. Independent variable should have two categories, and there should not be relationship between the two groups. That means it should be independent groups, and the dependent variable should not be. That means if it is not normally distributed across the two categories of independent variable, then we'll go with this type of test. And again, the distribution should follow the same shape, both right or skew. This again, it is here in Mann-Whitney U, but if you see, if the distribution is following the same shape, you can go ahead with the independent sample t-test also. So these are the two examples you can see here. This is the QQ plot of SGOT, and the two groups are like the myocardial infarction or the recurrent myocardial infarction and the first myocardial infarction. And if you see the plot, it is almost the same, the shape. So the hypothesis is, it says that the median of the two groups are equal, and the alternate hypothesis says that the median of the two groups are not equal. So I'll go to the questions. First, we'll see the independent sample t-test. So this is your so if I have to check the distribution of first, if I need to if I want to apply the independent sample t-test, means wants to see, like, I want to see mean SBP in two group, which is the male and female, BMI in male and female, and screen time. So how I can do it? So this is my data sheet. And for independent sample t-test, if you go to analyze, and this is the t-test. So click on this t-test and click on this independent sample. So if you click on this independent sample, then this window will appear. So this is your dependent variable box, and this is your grouping variable. So let's say SBP, BMI, let me see the question. SBP, BMI and screen time. So I'll move the SBP. First, it's BMI, SBP, and screen time was. So I know, like, what is the behavior of my variable from descriptive. So if you can recall, BMI and SBP were normally distributed. But for that, I need to check the distribution. So that I will go, because if you see here in the t-test, if you go with this assumption check, it gives you the overall. Like if I want to check with the QQ plot across gender, grouping variable is my gender. So it gives you an overall plot. It doesn't give you in the group. Like you have to check the distribution in two groups. So for that, I'll go to this explore descriptive, the way we have done in correlation. So I have to check these assumptions from descriptive. So I'll move this BMI, SBP, and the third variable was screen time. screen time. And this is your across, like I have taken gender. So now I have to check. I will uncheck this. You can just click on this medium and median. And here check for the QQ plot, box plot, histogram and density. And check for the descriptive. This is assumption. So it gives you the QQ plot in two groups, like QQ plot of BMI, SBP in male and in female. Similarly, the box plot in male and female. And similarly, the histogram in male and female. So if you see the BMI, it is like normally distributed in the two group, male and female. If you see, this is female and this is male. Similarly, if you come down, there's one outlier in male, but there's no outlier. So this is, I can go for independent sample t-test taking these two assumptions. Now if I come, and this is the QQ plot. So it is normally distributed in both male and female. You can see. So if you use the assumption testing of the Jamovi of independent sample t-test, there it gives you only single graph. But actually, you need to check the distribution in these two groups separately. And that's how you need to report it. Similarly, if you see the SBP, it is again not very normally, but approximately normal. You can see there are two outliers in male and one in female. This you need to report. And then you can see again, it is approximately normally distributed. So I can go ahead with the this independent sample. Coming to screen time, also it is supposed to be like normally distributed. Little bit of skew is there, and there are two outlier in female and 4 outlier in male. And again, you can take it like approximately normally distributed. So I have checked for these assumptions. One assumption. Now, the next assumption was your homogeneity of variance. So I'll go here. I will again move the screen time also. So screen time per day. Now I'll go and check for this homogeneity. QQ plot I have seen from the two different groups. So what is the value? Homogeneity test if the value of this Levine's test of equality of variance. Here also, if the p-value is more than 0.05, we say that there is an equal variance. Why? Because in null hypothesis, it states that there is an equal variance. So if there is an equal variance and we want that, so our p-value should be more than 0.05. So I'll check with this homogeneity of variance, and you see that in case of BMI, this value is less than 0.05. But SBP and screen time, this value is more than 0.05. That means equality of variance is met for these two variables. But for BMI, this equality of variance is not met. So if it is not met, then I'll go with this Welch. Can you see this Welch statistics? So I'll click this Welch statistics. So what you have to do, you report this student's T for SBP and screen time. So both type of T you can see here. For SBP and for screen time, you report student T. But for BMI, you have to report Welch T. This T, its degree of freedom and its p-value. And there's another option, which is the mean difference. So you click on the mean difference, the effect size, confidence interval of the effect size. You can click on the difference, mean difference, confidence interval also. Click on the descriptives and descriptive plots. All these 4. Wait for some time and it will show you. So this is the Cohen's d. First you see the p-value. So how will I interpret? For BMI, if you see, the p-value was not significant. So if the p-value is not significant, if there is no statistical significance, we are not going to report for effect size. Reporting of effect size only comes when there is a statistical significance. The way we have learned for chi-square. When do we report Kramer VN? We report Kramer V only when the value of chi-square is significant. Since here the value of P is not significant, so we are not going to report the screen time and the BMI, the effect size. For SBP, we may. So if you see the effect size, this is our Cohen's d. Now, before I come to this, let me take another. Okay, I'll come to this part also. This is homogeneity of variance. I have discussed this homogeneity of variance and regarding the Welch T. And this is the group descriptive. That means this tells you the number. There are 63 females and 107 male. And the mean value of this BMI is 23.72 in female and 24.41 in male. This is the standard deviation and this is the standard error. Similar for the SBP and the screen time. Now, if you come down, this is the descriptive plot. So this circle is for mean and these two lines are for the 95% confidence interval. And 95% confidence interval is mean plus minus 2 standard error. Remember? So the standard error which you can see, if you multiply this by 2 and if you like plus and minus this from this mean value, it will give you the confidence interval, value of the confidence interval. So this is a descriptive plot of BMI. This is the descriptive plot of SBP. You can see that there is no overlap. That's why they were significant. Here you can see there's a lot of overlap. And that's why it is not significant. And here also you can see there's a there's a overlap between the
Ma'am, could you please take up where there's no overlap, ma'am?
This one. This was the SBP. And that was significant. Here if you see the value, P value. SBP was significant. But these two are not. Have you understood, Dr. Ravi? This is the descriptive plot. Can you show me the chart? Okay. Dr. Farzana has asked some question. Overlap means difference is very less, na? If you see the 95% confidence interval, this is the mean and this is the mean and this is 95% CI. So like many of this male, this is coming under this female area only. That we know by overlap. Here if you see, if one ends here and then there was some gap and then this male, the values get started. That means their confidence interval also, there is no overlap. This is discrete, like this is placed here, this is placed here. But if you see this one, so you can see there's a lot of overlap here.
Difference by chance.
Like if the other, it would have started like this. Once it would have ended. For independent t-test should be use only one dependent variable against one categorical variable. We are using only one only. But we have moved these variables together. Like you can do it one by one. No problem. Like I will move these back.
Yes.
Then it will only tell you about BMI. But just for demo, since you can have like 3, 4, 5 variables here, you can have. But again, the problem will be like you need to click all the things. So you can go one by one. Let's say only BMI. So I'll explain BMI if here it is, p-value is not significant. P-value is significant. So the homogeneity of variance, that assumption is not met. So what I'll do instead of student, I will uncheck this and I'll click this Welch. And in Welch, if you see, I will report this. It comes like Welch T statistics. And then it will be the others will be the same, like group descriptive, mean, median, BMI, and then this thing. So this is for one. Again, you can move this
Ma'am, it
back,
is still
BMI.
showing a violation of the assumptions. Just a low p-value suggests a violation of the equal variances. It's
Mhm. Still? Yes, your low p-value suggests a violation of assumption. Yes, uske baad, what said you after that? What did you say?
Still we go ahead with it. Still we go ahead with it. Even if you apply the Welch T statistic, it is showing a low p-value suggests a violation of the assumptions, wherein the p-value is 0.03. So we still
P-value,
go. Okay, p-value with Welch is changed. Okay.
this is the p-value.
What difference?
That is the Levine's test p-value. This is the p-value of T statistics. And this is the p-value of Levine statistics, which is based on F statistics. It
Okay.
is
So they
different.
are both are different. Yeah, understood.
Yeah, it is
Understood.
T statistics and this is F statistics. The degree of freedom is also to see. Its degree of freedom is related to the number of individual, and its degree of freedom is related to the two groups, because there are two groups now. Independent sample, there are two independent sample. That's why this statistics is different and this statistics is different. This is this p-value. Let me explain.
Difference.
This p-value is the overall p-value. Means like the mean difference of BMI in male and female. If you see the mean difference from the descriptive, you can see, if I come down, mean difference you can see here also, like minus 0.69, this one. But from here, if it is not clear like which one is higher, then you can come down and see. So mean in female is 23.72 and mean in male is 24.41. That means what it does difference, female minus male. That's why this minus sign is there. And many times people ask like why there is a negative sign in the statistics and why there is a negative sign here in the difference. Why? Because by default, if you have written like it does 1 minus 2, female you have coded 1 and male as 2. So that's why female minus male, and since female are having less of BMI, that's why it is a negative sign. Otherwise there is no difference. The value will come as such only. So the p-value of Levine's test only tells you regarding whether you should report the student T or you should report the Welch T. So remember this always, there is a confusion in the participants and among all of us also. We are also, many times we have this confusion regarding the normality and homogeneity. Both are two different things. For normality, if that assumption is not met, you have to go with the Mann-Whitney. For homogeneity, if it is not met, you have to go with the Welch. I'll come to, so have you understood up till this point? Or any confusion? Then I have to show some more points also. Okay. Anybody like Dr. Lokesh is asking? Okay, that too we have seen. So now I'll go to the effect size. So before I move to the, I wanted to take this, this Cohen's d. This was the effect size. And let's see how do we interpret this effect size also. So remember, this effect size will be reported only when the value of T statistics is significant. For example, I'll move the SBP because it was coming significant. And I'll report the student T because the homogeneity of variance assumption was met. So the homogeneity of variance, if you see the p-value, the p-value is 0.906. That means the assumption is met. That means it's an equal variance. And if you see the value, 115 is the mean in the female and 123 in the male. That means there is a difference of, and that difference you can check from here also, mean difference of 7.47 millimeter of mercury, and which was significant. So if it is significant p-value, then I can go report the Cohen's d. So effect size in this case, it was 0.87. So 0.87 is a very good effect size. And we'll see how to classify this. Coming to, now again, I will take the, again tell you the effect size. So in the morning also we have learned regarding the effect size. So what is the effect size? Basically, we have learned that if there is a fire, yes and no. Yes, it will tell you statistically significant thing will tell you this. But if I say how small or big fire, then you have to go with the effect size. So for this also, again, we can see this analogy. I think, have you explained this? Have we explained this currency? Maybe in meta-analysis we have. Okay. So imagine we are trying to compare the price of a cup of coffee. Why this effect size? Why this effect size? So I'm trying to explain what is the need of this effect size. First thing we have learned that, it helps us to make decision, clinical decision or change in the policy that is again needed. But if you want to compare, so what this effect size does, it makes the comparison easy. So for example, if we are trying to compare the price of a cup of coffee across these different countries and each priced in its own currency, you can see here we have got Japan, France, UK. These are the country, and this is the price in the local currency. So if you see this, so if I ask this question, where is the price of these cup of coffee is the maximum? So what will be your answer?
Average
Because if I see, I can say in South Korea it is maximum because it is 5,000, but I cannot compare it. So what I have done, I have converted that into a US dollar because that is considered as a standard. So now if you see the price, I can compare now the price of coffee. And if you see which is the country having maximum price, so probably the Switzerland having the $5.3. So this you can, this helps us to understand, if we apply the exchange rate to convert each currency to US dollar, now I can compare the cost of these items across the country. Similar thing if I want to compare which drug is better in the management of hypertension, whether it is telmisartan or losartan. So I have conducted one study. I have given 50 patients, losartan to 50 patients and telmisartan to 50 patients. And then I see the mean reduction in blood pressure. So telmisartan, the mean reduction was -10, and in losartan, mean reduction was -12. So if I ask which drug is better, so what will be your answer?
We'll have
Yes.
to check for significant lowering of blood pressure. I mean,
Okay.
-2 is
both,
hardly any effect. Effect
yes,
size is hardly any.
true. Only a difference of 2. So I cannot say. Again, similarly, if I want to see the effect of a new drug, so one drug is saying there's a difference in blood pressure of 15 millimeter. Another drug is saying in diastolic blood pressure, it is mean change in the 5 millimeter. So now here comes the role of effect size. If the mean change in blood pressure is 15, but if effect size is 0.33, and the other one in DBP effect size is less, it is only if it is more, mean difference is less, but effect size is 0.42, then I will say that, yes, I will take that where the effect size is more. Similarly, here in this slide, the same previous example, -10 and -12, you have to see how, what was the standard deviation. And that's the formula of a Cohen's d. So in Cohen's d, what we do, we take the standard deviation into account, and what we do basically, we divide this mean difference by standard deviation, and that's the effect size. So the larger is the value, more is the clinical significance. So here the average reduction, this it will be more because the effect size is -1.6. So coming to this assumptions, we have seen in the independent sample t-test, there's an assumption of homogeneity, there's an assumption of normality. So if only homogeneity assumption is violated and normality is met, so what test you will apply? You will go with this Welch t-test. If only normality is violated and homogeneity is met, then you will go with the Mann-Whitney U-test. But if in any data set, if both homogeneity is violated and normality is also violated, then again your choice of test will be your Mann-Whitney U-test. So the ideal is when both assumptions met. That in that case, you know that you will go with the independent sample t-test. But in case of violation, if only homogeneity is violated, then you will go with the Welch T. But when normality is violated or both violated, then in that case, you will use the Mann-Whitney U-test. So how you will take the independent sample t-test decision? So if the data are not normal and the groups vary widely, then we have to use the test that doesn't care about shape or size. And that's the Mann-Whitney. So Mann-Whitney doesn't it doesn't go with those assumptions of the independent sample t-test. Now there was you must have seen that in the interface, I did not show you at that time. But can you see there is something known as the missing values? So if there are missing values, we have not covered the exercise of missing values. I will take that. But if there are missing values and there are two options in Jamovi, so how do you want to treat? So if the number of missing values are, let's say, very less, 1% or 2%, and you don't want to replace it. So in that case, there are two options in Jamovi. Either you can exclude case analysis by analysis, or you can use this option of exclude case list-wise. Now, what are these two options? So basically, if you go with this option of exclude case analysis by analysis, so this is also known as the pairwise deletion. That means Jamovi includes as many cases as possible for each individual analysis. And what it does, it will only exclude that particular variable where the data is missing in that particular analysis. For example, suppose I am analyzing this BMI, mean BMI in male and female, or I am analyzing this mean BMI in versus analysis like SBP means like hypertensive and the normotensive. So if the patient A that has got a missing SBP, but has got BMI and gender, and there's again patient B, which is like the variable is missing gender, but it has like BMI and SBP. So in analysis by analysis, what will happen? Like patient A, it will be included in BMI and gender. And patient B, since gender is missing, so he will be included in BMI versus SBP. So whenever you want to maximize your sample size, but in this case, there will be different denominator in different tests. So number can be different. The participant number can be different in different tests. So you go with this analysis by analysis. Another option is like exclude cases list-wise. That means what it does, it exclude all that particular row. So a case or row is excluded from all analysis if any variable is missed anywhere. So what it does, it generally ensures a consistent sample across all tests. So the same scenario which you have seen in the previous, like patient A and patient B, where the patient A was having missing value. So it will be if he has like missing value of systolic blood pressure, he will be excluded from all the analysis. Similarly, the patient B, if he is missing from gender, if the gender is missing, he is also excluded from all the analysis. So in that case, there is a compromise of the sample size. That means even if one value is missing, that whole row will be excluded from analysis. But again, if you want your consistent number of denominator across all analysis, like you are going for a publication or you are performing a regression analysis. In the regression analysis, you cannot have different numbers in all the variables. So for that, you need to go with this case by case analysis. So which one to use? So if you want to maximize your sample size for analysis, then your recommended option is use this option of analysis by analysis, which is the default. But if you want to use the same sample size across tests, or if you want to perform list-wise this regression, then you should go with the list-wise exclusion. For example, here I don't have a and this is just the screenshot I have taken. Like Analysis by analysis, you have to use this. Cases with missing gender. This I have already told you. So we'll go this here. So exclude case analysis by analysis. This is the default option. And generally we go with this option because we want to maximize our sample size. So this is for the independent sample t-test. Now coming to its non-parametric, this solves my issue mostly. Actually, what should be the ideal? So Dr. Farzana, it is up to you. If you want to if you have to perform regression, then you go with this, or either you can do the imputation, which will tell you tomorrow how to replace missing value in Jamovi. Because Jamovi, there is a way like you can replace, if you want to perform regression, you can replace your variable with either mean or you can replace your variable with mode. And that automatically gets replaced. We will tell you tomorrow. But again, for now, like you can use this option also if the sample is very less. But again, even if you don't want to compromise on that much sample also, you can use the imputation method. And we are having a demo probably tomorrow on that imputation method. We will delete many data from this data set only, and then let's see how it replaces. So that's why we did not want to have this session in the in the middle of this workshop. So probably tomorrow after having ANOVA, we will have a demonstration session of this imputation method, how to replace impute value, imputation. So if you have understood this, now coming to the next question. This was the normal distribution. So we have used the independent sample t-test. And again, here also you have to write all the assumptions. So if you see this, I have written here like outlier, number of outlier, homogeneity of variance, and then approximation. Like if you see this, I have used this like the mean SBP using QQ plot, which showed that the distribution was normal. Outliers were not significant, as evidenced by the visual inspection of box plot. I'm just coloring it with different color. Homogeneity of variance was assessed using Levine's test, and which was not significant or significant. And then this is very dark. And then you can write like, that's why you have reported the Welch T or a standard T, depending on that. And then you have to write like mean and SD also. Like mean SD of in the male and mean SD in the descriptive plot. You can also copy paste that plot if you wish to show that, especially for thesis, we encourage our students. So you can just click, copy and paste that. So let's see, I'll paste it here. So you can paste that graph, you can like make it small also, and you can show it. So this is regarding your write-up, how you will do the write-up. Coming to this is again BMI, the same this thing. Write-up is there same. Again, coming to like there's one question where I have to apply Mann-Whitney. So again, screen time. If you screen time across expense category. So let's see, expense category less than equal to 20,000 and more than 20,000. So let me see the variable. So if I see the expense category, average screen time, sleep duration, commute time. Monthly expense. So if you see monthly expense, I have got less than 10,000, 10,000 to 19,000 and 20,000 and above. So it is having 3 category. So I have to convert it into 2 category. So I'll go to this again, I'll apply transform. So I'll go to this transform. And here I will use that create new transform. Add recode condition. Here I may write like transform of monthly cat. Source variable is same, and then I'll have to see less than equal to 20,000. So I'll select the operator less than equal to 20,000. Use, I will write less than or equal to 20K. I will put an inverted, single inverted comma, else more than 20K. So I'll use more than 20K. I'll close this and press enter. So two category, it's there now. And then I'll go to this option. I'll move this screen expense category. So expense grouping variable. Grouping variable in my question is the expense category and screen time. So expense category is my grouping variable. This is my expense category. And so let me check regarding whether that variable, because there are two. Okay. So name is monthly expense, monthly cat. Okay. Monthly expense and monthly cat. So I'll go. This is not the variable.
ऊपर आ गया.
So here you change the nature of the variable. Can you see? I have not changed. I'll go to the data. And I'll edit this. Okay, nature of variable. Here you can change it to nominal. So monthly expenses, I will write 2 category. So that will help me to remember. So again, I'll go here. Monthly expense 2, I'll make it as a grouping variable, and screen time. So if I'm taking screen time as not normally distributed. So screen time here. And then I'll click on this, instead of Welsh and student, I'll click on Man Whitney U. This is the QQ plot, you can just see. And if you see the homogeneity, again, this is assumption is met, but again, since I cannot, I have to go with this Man Whitney U because I am assuming that data is not normally distributed. So median, it gives you like 180 and 120. This is the median in the two groups. And the basic is like you have to report this Man Whitney U statistics. And again, it is significant. If you see this Man Whitney U statistics, it is significant. And the effect size, if you see, effect size, it is the rank by serial. So in case of because I remember I said that it converts the values into rank. So it compares the rank. So that's why it is not the Cohen's d, rather it is the rank by serial correlation, which is used in case of Man Whitney U. So it is 0.25. So like again, if I go back to this, coming to that Cohen d. So yes, Cohen d, I was discussing that independent sample t-test. So how that formula of Cohen d comes, like in the numerator, it is the difference of the mean. And in the denominator, it is the pooled standard deviation. So you all can do this exercise that from this table, you can calculate the Cohen's d also. I did not deliberately, I did not give that exercise because I thought maybe it will be, I don't know. So let's, if you In the independent sample t-test, what you can do, if you move this, let's say gender and SBP, or you can do right now, or at home also, this is an activity for all of you. SBP, and let's say grouping variable is gender.
Ma'am, just a minute, ma'am. You had said the variances, the assumptions were not being, sorry, assumptions were met since the p-value is not significant. Still, we went ahead with this, ma'am.
This one,
Hmm. Because in this also the assumptions are, I mean, the p-value is more than 0.05, which means that the violation of assumption is not there.
yeah, so that's why I'll go with the student T. Yeah, this example I'm showing you to calculate this Cohen's D. Cohen's D, how to calculate the effect size. So since you have this standard deviation, this descriptive table, if you see this descriptive table, you have got a mean and mean of mean 1 and mean 2, and you have got a standard deviation 1 and standard deviation 2. So from these 4 values, you can calculate this value. This one. Okay, this Cohen's D. This value you can calculate. So for that, I just changed the interface. Initially, I was doing it on the monthly expense category and the screen time. Remember? But I just shown you this formula of Cohen's D, and using this, you can calculate the Cohen's D. That's why I came to this. Now, what is your question, Dr. Ravi? You said that even if the assumptions are violated, here the assumptions, homogeneity assumption is met, and we have checked the SBP with gender. That's why I have taken the student T. In case if you are talking about this, like I'll move this back, this to here, and I'll take in the grouping variable, it was the monthly expense having 2 category more than equal to more than 20,000 and less than equal to 20,000. And the screen time. What was my another variable? Screen time. So you are saying why I took screen time as a Mann-Whitney U? That's what you want to say.
Yeah, ma'am, can you just first put it, ma'am? Let's see what the homogeneity of variances say, then
Okay,
I'll
okay.
then
Screen time. So you want to say like here the screen time is here the homogeneity of variances assumption is met.
Correct. Still, you have taken a Mann-Whitney U test. That's my query.
Yes. Why? Because I am assuming this if the homogeneity of if the assumptions of normality is violated, let me check first. You check the assumption. So if you go with the descriptive, this if I am considering that this is not normal, you can do for demo. Let me shift any other variable. Probably let me.
Okay, ma'am, we'll continue with this.
No. Otherwise, let me average commute time. Let me see its distribution. This is not normal. Okay. Ideally, this should not. Ideally, I should go to the exploration, and I should check it in the 2 category, male and female different. I mean, this monthly expense too. But still, some rough idea you get from this also. So if average commute time, if I want to see whether the average commute time, what is the mean commute time in the people who are spending more than 20,000 and people who are spending less than 20, less than equal to 20. In that case, let's see. I will go right now. It's by default, it's the student t-test. So I will see this homogeneity. So right now, nothing is here. So if you see, it's the assumption, it's 0.55. Okay. So this is met. But if you see first we check the normality, because if you remember this, that's why I've shown you this slide. No. Yes. If only homogeneity violated, not the normality, then you report Welch t-test. Or if only normality violated but homogeneity not, then you go with Mann-Whitney U, and when both violated, then also you go with Mann-Whitney.
Understood. Understood.
That means if my normality is violated, even if my homogeneity is not violated, because it is a non-parametric, this Mann-Whitney U. And for me, normality comes first and then comes homogeneity. So if my data is not normal, then even this Mann-Whitney U is more flexible. So in that case, I will not go. This homogeneity comes with the Welch or the standard T. With non-normal, it will always be Mann-Whitney U. Okay. So that's why you have to report in this case Mann-Whitney U. I've changed the variable. And now you can see average commute time. So it is 42 minutes and 47 minutes. And then this is your mean difference. So there's a difference of 5 minutes, which is not significant. And that's why you will see that overlap is here also in the people who are spending more than 20K. And again, if you see the number is also less, more than 20K, only 37 people are here, and less than equal to it is 20. It is more number is there, but still if you see it is 42 and 47, so that much difference is there. But since the number is less here, you can see, remember how we have defined the formula of standard error. Standard error is very high here, 5.49, because sample size is less. So if the sample size is less, it will be not, that confidence interval will be very wide. That we know. That with lesser sample size, your confidence interval will be wide. Why? Because for standard error, remember, it's the standard deviation divided by under root n. So n comes in denominator. So if there is a small sample, the denominator will be high. Okay. So that's why this is the interpretation of Mann-Whitney U. Have you understood up till this point? The assumptions, the cases, what to apply, when, case-wise deletion, list-wise deletion, Welch T, student T, effect size, Cohen's D. Cohen's D, there's exercise which I want all of you, if you have time at home today, please try to calculate it. That Cohen's D in SBP with the 2 gender category using this formula. Not this one. This one. Here the standard deviation we take as a pool standard deviation, and the pool standard deviation formula is this one. You like n1 minus 1 standard deviation square 1 plus n2 minus 1 standard deviation square 2 divided by n plus n2 minus 2. Maybe people like Farzana who are more interested in doing, you can try that, how to calculate. I tried doing it and it was coming. So you can use that. Now there are some variations of Cohen D. Like for paired sample, you can do that like before and after. We'll see that how that Cohen's D is calculated in case of a paired sample t-test. So I'll tell you when we'll come to paired sample t-test. So I think we can go to the breakout room and we can practice this independent sample t-test. Then we'll have session on the paired sample t-test. Any question before we go to the breakout room?
Ma'am, with this Cohen D, so how we can interpret the this one, ma'am? Like small values of Cohen D.
Yeah.
How we can interpret?
So I think, let me show that. I think we'll share that slide, but again, it is, I think in the morning. So like 0.1, 0.3 and 0.5 is there for the chi-square and correlation. If you see the Cohen's d formula here in this case, it is in case of independent sample, it is 0.2, 0.5, and 0.8. So like independent sample t-test and the paired sample t-test, remember it is 0.2 and 0.5. It is more like the Kramer V. Kramer V we take 0.3. But instead of medium, here medium is up till 5. And after that 0.8 and more than that, it is the large. Did you get it, Dr. Radha?
Yes, ma'am. Yes, ma'am. Ma'am, one more thing. Can we just apply this one in meta-analysis also? Effect size is coming the same. Can we apply? No.
Meta-analysis,
Different.
do you have to write like whether it is medium, large? Like in case of while you are entering the data?
Okay.
Because
No, effect size, it is also, we are telling the terminology effect size.
yes, in meta-analysis, definitely the whole meta-analysis works on this effect size. So
Yes, ma'am.
in Jamovi, whether you want to take single effect size means, that's what we told you. The meta-analysis using the odds ratio, meta-analysis of hazard ratio, taking that as effect size, or meta-analysis of like 2 by 2 binomial or proportion or correlation. I think we have shown all the
Yes.
did you attend it?
Yes, ma'am. Yes, ma'am. Systematically. Meta-analysis.
Yeah. So there we have shown like effect size. These are the effect size. There generally, there's no column where you will enter whether it is a small or a medium or large. You only enter the value of these effect size.
Yes. Ma'am. Thank you. Ma'am.
Whatever is reported in the literature. Or
Yes.
many times, if it is not reported, you can mail the author and you can ask also. And people who are very enthusiastic, they go and they calculate also from the data.
Yes, ma'am.
So it is stepwise. Like initially, when you plan to do, you only do on the reported data. Then when you plan your next meta-analysis, you can go ahead and you can yourself calculate. Right.
Thank you. Thank you.
My pleasure. So if it is any other question before we go to the breakout room? Let's see. First they'll practice this. Otherwise,
How many breakout room we should?
I think 15. So
they will start sharing and just 2 ही कर रहे हैं, 2 ही करते हैं.
So yes, we are having 2 breakout rooms. So yes, I think that breakout room time was over, Dr. Geeta. So you were doing right. The only thing is now you have to go to the independent sample t-test and check those two, like monthly expense which you have created and the average commute time. The same you were about to do, and then that this breakout room that got closed.
Okay,
So
ma'am.
don't worry, you can practice that again, seeing the video. You have to check the assumptions. You could transform it. That's good. And always, remember to use single inverted comma whenever you are defining a particular variable.
Okay, ma'am. Okay.
The paired sample t-test.
Yes, ma'am. Paired sample t-test.
I'll So now coming to this paired sample t-test, and its non-parametric counterpart is the Wilcoxon sign rank test. So in this session also, we'll see some basic concepts and the research question for which we need the paired sample t-test, the assumptions and hypothesis, the commands and interpretation, and the summary of overall this paired sample t-test. So this is very much similar to the McNemer. The example which we have used in McNemer, we have used the same example here. But the only difference is there we have made it to a categorical variable. Here we are measuring it on a continuous scale. So like systolic blood pressure, if I'm measuring this systolic blood pressure, I'm measuring it in two occasions, like summer and winter, or I'm measuring it under two different conditions, like before workout and after workout, or I am measuring it in the right arm and left arm, two different sites from the same individual, or by two different machines or instruments. So these can be the example of paired data because it's a paired sample t-test. So the two observation should be on the same individual, and that's the paired t-test. So what are the study design for which we can use this paired sample t-test? So the first type of study design can be the participants are either the same individual tested at two different time points, like maybe the season or pre-post intervention, or it can be the participants tested under two different conditions on the same different variable. Like in this case, blood pressure machine, again, the different conditions means like automatic blood pressure machine or a manual blood pressure machine. So we may use the independent sample t-test. So here, like you can see, there are 5 participants and they are being tested at two different time points. So here we have taken the median intake of calorie, and after 6 weeks dietary modifications program also, again we measure the median intake of calorie or mean intake of calorie. Similarly, like in the same 5 people, we have given first intervention, that is the health drink 1, and we have measured the outcome, that is a kilometer run on the treadmill. And after some time, maybe because we need some washout period time, we have given the another intervention, that is the health drink 2, and we have measured the kilometer run on the treadmill. So it is the same paired value for two different two different intervention. Then also we can use the paired sample t-test or two body parts of the same individual. If I have applied the medicated cream on one arm and non-medicated cream on another arm, so the outcome variable in this case, if you see, this is a group of 4 kids. So I have applied a medicated lotion in one arm. Let's say this one is the medicated lotion and this 2 is the non-medicated lotion. And I am measuring and both are having the dry and red skin, and I am measuring the diameter of redness after this application of this medicated and non-medicated. Then after a week, if the researcher measures the redness, measure as a maximum diameter on each arm. And if we want to know whether the medicated lotion is better than the non-medicated lotion. So my outcome variable here is the diameter of redness. And my paired data are the medicated and non-medicated, but they are applied on the right and left arm of the same person. So what can be the research question? So if I want to know that whether there is any change in the scores or the dependent variable in these paired observation or not. So what are the research questions? So whether there is any mean difference in BMI value before and after a 6 weeks exercise program, or I want to see the pain score measured on VAS scale before and after surgery, or is there any difference in marks obtained in pre-university and university examination of MBBS students? So in all these examples, what we have seen, that there is a continuous variable, which is the dependent variable, and we are measuring it at two different time points or under two different conditions in the same individual. That means they are the paired data. So if we see the study design again, the same McNemer, most common the pre-post study type of study design we use, and it is also known as the paired sample t-test or paired t-test. So coming to the underlying assumptions. So again, here the dependent variable is measured on the continuous variable, the way we have learned for the independent sample t-test. And here the independent variable that consists of a two different category. It can be related groups or it can be matched pair. And there should not be a significant outlier in the differences between the two related groups, and it should be normally distributed. And this we check on the same interface of the paired t-test. We need not go to the descriptive. Why? Because here you see the distribution of the difference in score. So in SPSS, if like initially we used to conduct this SPSS workshop, and there you need to create a new variable where you need to create this difference like pre and post, and then we used to check the normality. But in Jamovi, by default, it gives you the normality means QQ plot of the difference in score, and that we check. So what is the null hypothesis? So basically, null hypothesis states that the population mean difference between the paired value is equal to 0. And the alternate hypothesis says that the population mean difference between the paired value is not equal to 0. So coming to the demo of its non-parametric is the Wilcoxon sign rank. So again, if the assumptions are not met, we will go for the Wilcoxon sign rank. So this is the question. So I have to check the distribution of difference of these parameters like PHQ, 4 score, pre-post. These are the 3 variables which are having pre and post score on the same individual. So I'll go on this Jamovi. I'll click on this t-test, paired sample t-test. In the paired sample, here you have to move the variable together. So what you have to do, like, and PHQ total score, press Control on your keyboard, and then come to PHQ total score post, and then shift these 2 variables. So there's a slight difference. You have to select both these variables together and shift them to this. And now here you have to check for the assumptions. So first I'll check the assumptions. So there is a QQ plot. Here there is no concept of homogeneity. Why? Because it is the same population which are measured twice. So the 2 groups are not different. So that's why there is no concept of homogeneity of variance. So that's why only one assumption, that is the normality. And this you can see whether it is normal or not. So I think you can consider it to be across these, this is across the same line. So maybe I take it as a normally distributed. And then this was the PHQ total score. So then I will go with the student t-test, the mean difference. So if you see the mean difference, it is the minus 0.84. This is the, and you can see the effect size, descriptive, and you can see the descriptive plots also. So if you see the effect size, this tells you the effect size again. This is the Cohen's d, 0.24, and you report this only when the value of P is significant. So this is a small effect size because it is 0.2. And coming to descriptive, if you see the mean, it is 3.15 pre-intervention, and this is the 3.98 is the post-intervention, PHQ total score. This is a descriptive plot, both, and then so you report all this. You can copy paste this table, and again seeing the other variable. Let me see the any other variable. The other was, I will move this back. The next was anxiety. So I'll select anxiety. I'll press Control and anxiety post. And this depression also, pre and depression post, I have shifted. So that I can check both in the single go. And then I can check anxiety. So if you see, first see the assumption. So anxiety is also a little bit different, but again, you can go with this paired sample t-test, and you can see the descriptives also. So descriptive, the mean is 1.56 and 1.92. So there is an increase in the anxiety score. Here also there is an increase in the mean anxiety score after the intervention. But this is, I said that this is a dummy data. That's why don't go by whether it is increase or decrease. You just see whether whatever is the difference, whether it is significant or not. So if you come here, it is also significant. The mean change in the depression score here, and whatever is the value, you see that Cohen's, again, effect size is very less. It is 0.17 and 0.18. So it is a very small effect size. Any other variable? Let's see. We don't have any other variable actually, where we have got pre and post. So that's why Wilcoxon sign rank, we'll see if we have got any other variable, then we may show you. But otherwise, this is the interface of paired t-test. So the only thing is, it has got only one assumption, that is the normality. And when you move variable, you have to select both the variables together and move it to this window. Otherwise, the rest is same. The descriptives and the descriptive plot, etc. So any question? In this paired? Okay. If not, then we will share the recording and
What is the interpretation I use?
same thing here also.
Difference was homogeneity and
Difference is here the overlap. You can see
पहले और बाद का वहाँ दो ग्रुप थे यहाँ
pre and post.
सेम ग्रुप है यहाँ अलग अलग टाइम पे
Same. Slight overlap is here, but again, since the means are like far, here you will find that it is significant. Here it is not insignificant. Both are significant p-value.
%95.
What is 95%? Effect size, mean difference.
Mean difference for 95.
Can I see the question?
नहीं, some I was.
Okay. So have you understood this paired sample t-test? Then you practice this. We'll meet tomorrow at 10 o'clock. And we will see, okay, Dr. Lokesh. So do we decide on normality based on visual representation alone? Generally, here in case of large sample size, yes, visual and the histogram also. But like if you want to do it histogram, then you need to create a new variable here. Okay, so let's see. Since you have asked, I will go, since it doesn't give you the histogram. So if there is a confusion, so what you can do, you go to this data and you create a variable. That's what we used to do in SPSS. So what I'll do, I'll create another variable and let's say, I will use this compute variable. I don't know how many variables. Let me delete. So I have come to this variable. Let's say it is the difference of PHQ score. So what I'll do, I'll select this function. PHQ total, pre, and PHQ total post. PHQ total score post. And I'll press enter. So I've got this difference. Actually, on this variable, I need to check the distribution. So I'll go to this descriptive analysis. This you can do with the anxiety and for depression also. Go to exploration, go to descriptive, move this variable, difference in score. And then check for the histogram density and QQ. So you can see this is the histogram, and this is the QQ. So subjective way of interpretation is the way. So you can take help of these two, both the histogram and the since if it is not clear from many times from in QQ, it is appearing somewhat very different. So in that context, you can see this histogram and density. So it is up to you. If you think that it is, and for all these, we always say it is approximately normally. So you will never have a very well-defined, histogram or bell shape. But since you can consider like it is tapering towards both the end and in the middle, it is showing something like a bell shape. So you can take it as a histogram. So you can use two ways. That's what I said. In subjective interpretation, you can use more than one way to supplement your, decision of considering your data as normal or not normal. And in paired t-test, it's the difference in score on which we perform the normality. So that's how you can do it. I think Dr. Lokesh, is it clear now? You have written thank you. That's when I am considering that you have understood. Okay. Okay. So if it is clear, then we may conclude today's session, and we are meeting again tomorrow with ANOVA. If time permits, we will have repeated measure, and we'll see the data imputation, because ANOVA it's a big session. I mean, it takes time. So we'll see what all we can cover. So, okay, you will get the recording of the session and the PowerPoint presentations also. And see you all tomorrow at 10 o'clock. Today, try to do this calculation of Cohen's d if possible. If not, that's okay. So I am